might things might get technical, and yeah, we'll have a recording. So much. Did you guys have fun at Tony's last week? It was kind of neat, right? So a lot of that stuff is built on top of this open sound control protocol, which is, many of you maybe have uh, experimented with it. It's in other classes. It came up a couple of times during the presentations. A few people are thinking about using it. Essentially, what it is a network protocol um, that's built on top of UDP, which is a type of networking technology. Um, and it is a standard way of communicating between different applications. And there's a little bit of a history inside of the slides today. The slides. It was invented at UC Berkeley in CINMAT, Center for New Music and Audio Technologies, in the late 90s. And it was initially developed for controlling synthesizers using, I've held this up a dozen times, but like different types of controllers, right? And initially it was tools were developed so that you can control Maximus P through this stuff. But since then, we have OSC integrations in almost all of the different creative coding languages that we use at school and wherever. So, inside of processing, inside of Touch Designer, Max, of course, Unreal, Unity, all of the VJ softwares like VDMX and Arena, Mad Mapper, they all have open sound control integrations. Okay. Um, and so so inside of our augmented interfaces, so OSC looks like this kind of. It has this kind of syntax with these forward slashes and an address, okay, followed by a value. Uh, this is wrong. Okay, so what this would do essentially would send the value 0.8 to the LED level address, then to a sub address called 1. So imagine you have 8 LEDs. And you have data that's being generated randomly in your Unity experience. And you wanted to send that data out to 8 separate LEDs. You might construct your OSC messages like this, right? Where this 0.9, 0.8 is some variable that comes from maybe a slider or the distance between your hand and a game object that you're approaching, okay? There have been a dozen, and stop me whenever you want. So there's been a dozen, a ton of amazing OSC projects. Here's one that I really like. It's called Face OSC. This came out in the early 2010s by Kyle McDonald. It was a way of controlling OSC using your face gestures.
Hey, this is then you might want to find a darker
Oh,
background
and let
or
me
light
hear
yourself
the
differently. I'm
sound.
routing it into Reason here
Share. Oh, it
using
is sharing.
the parameters of my mouth width and height to control a formant filter. I'm also controlling a couple other things. So my face rotation is controlling the amplitude of chorus effect, and my distance from the screen is controlling the overall volume.
So you get the picture. It's a way of connecting things that maybe the developers had never envisioned connecting them together, but they enabled OSC. Therefore, anything that can send OSC can control that particular synthesizer. In this case, it was Reason. So this person, Kyle, made something that sent these OSC packets with the face data. Touch OSC is also really cool. So if you want to build like a custom interface for your Unity application, you could do that with Touch OSC, which it's an app. I think it costs like $10 or something, and you can build custom interfaces on the app and then on a desktop application as well. You can like upload your own designs to the mobile version and then send OSC using your mobile device to your Unity application. Maybe you want to make a custom controller with an iPad or something like that. So there's also a huge list of different OSC projects here for you to take a look at. And then, like here up at the top, just maybe just a couple of different things that inspired my own research into this kind of stuff and my own experiments. The first kind of thing that I saw was I visited the Fluid Interfaces group at MIT Media Lab, and they were doing some really interesting things with physical computing hardware and like this idea of like Internet of Things, right? And they're doing interesting stuff with Unity and augmented reality. This is kind of why this OSC lesson is building off of this augmented reality lesson that we did last week.
Provide us with a flexible graphical user interface that lets us share and interact with apps and other people. However, a graphical user interface needs our full visual attention. A tangible interface like a light switch, in contrast, can be operated just by muscle memory and the tactile feedback. Smarter objects can combine the tangible interfaces with the flexibility of graphical user interfaces using augmented reality image recognition. The smart device only requires a processor and a Wi-Fi connection to a server that binds the tangible interface with the actions of a graphical user interface. Smarter objects can enhance the concept of a traditional radio. Here we have a radio with a volume and a tuning knob. But we expect more. Nowadays we expect a rich media player. Therefore, this radio has a second graphical interface layer which let us access all the functionalities we expect from a modern digital radio. Since the graphical layer is tied to the tangible interface, all changes on the one are reflected on the other. Once we want to change a tuning spot, we select the song we want to place on it and drop it on the spot. We have now reprogrammed the radio, and we can use our new selection with a tangible interface. Such an interface can provide online radios and music services, the favorite playlists, and even alarm events could be included into the tuning knob. Once programmed, the device can be operated without a screen. If we want to listen to a song with a better speaker, we can just draw a line from the radio to the speaker, and those devices become instantly connected. Tap the line again to disconnect. This separation of interactions into tangible and graphical interfaces is possible because the most frequently used interaction can also be applied on a door opening system, whereby a virtual access system grants access to the door. Or enhancing a simple light switch, whereby light switch only triggers on and off, but the graphical user interface changes the light color. We envision that a virtual interaction layer supports all interfaces and interaction one can perform, with toys, within one's home, in the garden, or at work.
Yeah, so there's some really kind of interesting things you can start to think about by combining this augmented reality layer with graphical user interfaces, and then also having these UIs talk to not just the virtual environment, but to physical objects using OSC. And this was using Unity and using Vuforia, like what we did last week, and using an image target to control like this graphical this GUI here, which is a slider.
That looks perfect.
And then allows the user to interact with that slider in virtual
That's very
environment
cool.
and control send OSC over to a Raspberry Pi that's dimming this light. So, a couple projects brought up wanting to send data from Unity to another application like Max. This will kind of cover that, although we're going to kind of like focus on the AR aspect. And then also we will, a couple projects brought up maybe sending data from a physical device to Unity. So we'll also cover that. That might come up a little bit more next week. You could check out this project on your own time. This is the Folk Computer people, and they're making really cool augmented interface computing objects. And I just included another piece by Tony Dove here. This was the piece that we did before the current one. This was like a robotic installation, and it had a bunch of LED lights, DMX lights, robotics, as you can see, and these were all also controlled over OSC, networking a couple of different computers together. Ones that would control the robot, ones that would control sound, and ones that would control the video playback. So, kind of taking a step outside of the technology, what can you actually do with it? A lot of times when you're running these installations that require multiple devices, OSC is the way to go. There's a few different ways to send data out from Unity to physical devices. Another way to do this would be not through OSC, but through just using the serial port on your computer, the USB port on your computer. And if there are folks that really want to look at this together, we can. But here's a tutorial that kind of like talks about how to
Is
connect an Arduino
It is
to Unity
joystick and
for
the
making
rotation
custom
switch, all
controllers.
the
You could do
X,
this
A, Y
wirelessly
axes
with the
are
way that we're
working
doing it.
fine. So bidirectional communication with the serial port is successful.
Okay, this is
Today I made
also
bidirectional communication between
kind of like a smarter object idea that the MIT people are doing, where like the virtual object presses the on switch and it turns a physical light on. Okay, so essentially OSC is a great choice, not just when you have to connect computers together to have them synchronize different information about the state of your experience, but it's also a great choice if you have to pass information between two applications on the same device, on the same computer. Okay. So, we might want to send data from Unity to Max, for example. Let's look at how to do that. I gave you an example project up at the top here, this augmented reality project. And so we'll just I'll walk you through how I made that. I'll demo it first. And then we'll save this thing with the microcontrollers for next week. But all of this stuff down here talks about how to send and receive data from these physical computing devices. So basically what I'd like for us to be able to do by the end of class is to have an understanding of like mostly how to send data and receive data from Unity using this ext OSC asset. So if you open up that project, I made some I had some fun making image targets today. And so these are like good image targets because they're very asymmetrical. There's lots of fine detail in them. These are numbers 1, 2, 3, Z, M, and T letters, Z, M, and T. And so, yeah, maybe what I'll do is I'll share these image targets on the page, on the class page. But you have the 2 images that I am using for this example in the project already. So if you open up that project, you can also just create a new scene inside of, if you want to follow along and build it from scratch, you can also just create a new scene inside of your existing Vuforia project. However, if you're using that project that I sent you, then just make sure that when you open it up, that you go to the scenes folder and you open up the OSC AR folder. If you are using my example scene, you will have to put in your developer credentials in your app license key like we did last week. So let me grab my Vuforia license. I had to delete it to send it to you because if everybody uses my license key, then they suspend my account, which I discovered from previous classes. So if you somehow pause the video and copy down this long code, letter by letter, alphanumerically, you could get me into trouble, so don't do that. Okay, so that's clear what I did there, right? Like you need a license key to be able to use Vuforia. And essentially what I'm gonna do is I'm gonna show you how I'm gonna basically have 2 image targets. And as the image targets get closer together, they will send an OSC message out, and Max will pick that up, and it will, so this is Max. This is the new Max 9, which I'm really excited about. So it will print the distance between the 2 image targets frame by frame. And I'll show you the code. And maybe we could speculate a little bit on how you might use this in a project. This is like a really basic example, but just shows how that communication works. I've already done this for you, so you don't have to in this example project, but I am using this asset, this free asset called EXTOSC. So you'll, of course, need to click download or open. Should say download for you if you haven't downloaded it before. Open inside of Unity. And then click the import button when that package opens inside of Unity. And it might ask you to install some other dependencies. Go ahead and do that. And then you can create your basic AR scene with an image target prefab, right? So we did this, it's been a couple weeks now. So this is just a quick little reminder, but all of, you need an AR camera inside of your scene, which you can create by right-clicking and going to the Vuforia tab and choosing the AR camera, and then make yourself a couple of image targets. And that will create one of these prefabs. I've renamed this one transmitter just to kind of organize the scene a little bit better. But these are both image target prefabs with little cubes on them. Okay. And I'm just kind of giving a recap of kind of mostly what we did last week so far. So stop me if any of this is confusing, or and I can't see the chat, so you have to unmute yourself if you have a question. But what I've done was I've just dragged my image target onto the image target prefab, right? So now, so it knows what image to track. And I've done the other image for this other image target. And all I've done was added a cube as a child to both of these image targets so that the cube pops up when the image target is recognized. And there's also a script on this cube, on this transmitter object, right? So there's like everything we do, there's 1,000 different ways to do it, always. So this is what made sense to me, but in this for this demo, but essentially there's a transmitter script which transmits the distance between this cube and another object prefab, right? So I've made a public game object inside of the script and called it other object. And we'll look at the script in a second. And I've dragged this other object onto that place so that the update function can calculate the distance between this object and that other object and send it out to OSC. So before we jump into that script, also just kind of highlight there's an OSC manager. And so I just made one of those by creating an empty game object, calling it OSC manager. It doesn't need to be called anything special, just for organizing purposes. And I've added the OSC transmitter script to this OSC manager empty game object. And the ext OSC package that we downloaded that handles the OSC has a bunch of examples, and this example that I'm making is kind of just hodgepodging this getting started tutorial scene. And I don't need to save that scene. So you'll notice that the getting started scene inside of the OSC package we downloaded has an OSC manager. It not only has a transmitter script, but it also has a receiver script. For this example, we don't need to receive, we just want to transmit. And we also have a game object that just transmits some message at a specific address. Going back to my introduction of OSC, remember every OSC message is sent to a specific address, right? And then in our receiving program, that's how we kind of parse out the data so that we can send these values to specific things like synthesizers or opacity layers in my VJ mixer or what have you. This is all being recorded, so if things aren't making perfect sense, you can come back to this video. Okay, so I'm just gonna jump back inside of my OSC AR scene, and I've done enough talking. I'm gonna get my image target. I have an iPad with one image target. And maybe just one thing I'll highlight. Oh, I'm just gonna. Okay, so I have this one image target. Okay, so there's my cube. And then have my other image target. Okay. And you can see in my console at the bottom left hand, you can see that I'm sending distance values now. I know it's quite small. I'm gonna Okay, so you can see me, I'm sending distance values, and I'm gonna open up Max. Okay, and you could see those values streaming in. And I'm gonna move my phone. Let me kind of shift this over a little bit. Okay, so I'm gonna move these closer together. You should see these values get smaller, right? Because the distance between these two things is closer. So I'm gonna move them apart now. And there's obviously some tracking issues because of the reflection on the iPad and light, but we have something working. We have something getting smaller as they get closer, the distance getting less, and farther as you move away. Cool. And so what we can do inside of our receiving application is we could then start to route out that data in different ways. So now, instead of printing all of that data with this ugly address at the beginning of it, now I might want to route out that data, that address to this specific variable. And, you know, like you might imagine, we might also have a second address that we're sending data to, and we can route that number out to this other location. And so now if I do my image targets, let me close this, do this, do this, and do this. Wait a second. Hey, kitty. Okay, so now if you take a look at the Max screen, you can see that I'm routing that number out into a number box. So I have something that I could, you know, now scale and map to something else. Like this is cool. And there's obviously some cleaning up on the AR side that I need to do, like turn off extended tracking, right? Remember we did that. So I'll scale values between like 0.3. It seems like they can never get totally close to each other. So it seems like my minimum, seems like my minimum is about like 0.3 and my maximum is like 1. And I'm gonna scale that to be values between like 440 and 880, which all turn into a frequency, right? And I want to make sure that I clip my my values to be in that range. This isn't, a max lesson. This will be different for whatever application you choose to kind of like route your data to. But I'll use rectangle wave, and I will send the frequency there, and send this out to my speakers. And this looks different. That's cool. Zoom. Wow, they changed the way this looks. Interesting. Okay. Cool. This is the new max. So, whoa. Okay, so you can hear that. And okay, you know exactly what's gonna happen, but we have to see it anyways. Whoa. So obviously silly and very basic, but you can see how, yeah, this is just yeah, you could start to kind of imagine the different things you can start to connect together, just previewing like what that communication looks like between the two applications. So I'll save this with for us, and I'll put this on the class page. Um, and this is going to be called, what is this called? This is called Unity to Max OSC. Okay, so I'll throw that on there. Right. And so what's happening here? Okay, so there's these two image targets. What you might notice is that when um when I start the scene, this my basic unit, my basic Vuforia scene, this is the cube that becomes visible or invisible, depending on whether the image target is being seen. And what you'll notice is that it's this mesh render that turns on or off depending on if this is being seen or not. Okay, so you'll notice that just by showing the image target to the camera, it turns the mesh render on and positions the cube in the appropriate space. So I'll take that away. And this is on extended track, so it's going to take a second for this to go away. Go on. I could just take this off. Tracked. Let's do this. Tracked. Tracked. Okay. So, right, so it's noticed, it turns the mesh render on. It's not noticed, it turns the mesh render off. It gets noticed, it turns the mesh render on. So the reason why that's important is because we can use that. We can ask this game object. We can say, is your mesh render on? Because if it is, that means I know that you're seeing your image target. Okay. So let me go ahead and open up the script that I modified from one of those examples. Okay. And okay, so we have I added a public game object, right? And I called it other object. And that's where where we get that field that we can drag our other cube to, right? The address that we're going to send to is at example /example/1. If I have multiple, cubes that I want to check distances between, you can imagine, that I might add another address here and call it address 2. Forego that for right now. And that's, of course, the address that our Max application is looking at, right? Example /1. That's how it knows where to parse and place that floating point value that's coming to the address. We also have a public OSC transmitter, and we have to basically for every transmitter, we need to drag our OSC manager there, and that's how this cube with the transmitter script on it knows where to send that data. So we haven't talked about this yet. Every OSC setup needs to know the IP address. When you're sending, you need to know what IP address to send to and what port to send it to. So if we're sending to the same computer, the computer that we're working on, the IP address is always going to be this 127.0.0.1. If I want to send to another computer, it has to be on the same Wi-Fi network. Has to be on the same Wi-Fi network. But I could find that person's IP address and place it on there. And so typically you do something like you go to your Wi-Fi.
Bruce.
Okay, that was my dumb mistake. I turned off my Wi-Fi, showing you my Wi-Fi settings. And it still is recording, so that's cool. Okay, so yeah, the other IP address, you would typically, just go to that. If I'm sending something to myself, I might just need to pull up my IP address and type that into the settings on my other device so that it can send to my computer. Oh, and I'm not sharing anymore, of course. Share. Right, sorry. So what I was saying was going to the Wi-Fi settings, going to your Wi-Fi network, getting the details and grabbing the IP address. You can also, there's some fancy terminal commands too that you can run that'll give you your IP address, but this is good. So essentially our OSC manager, says, okay, we're going to be dispatching these messages to this local computer, this very computer, and you're going to use port 7000. You could change this. This could be port 7999, 12384. I forget what ranges the ports go between, but you're safe in the kind of like high tens of thousands, and there are some ports. Another kind of caveat, if you're at school using the university Wi-Fi, you will have problems sometimes. And so I don't know, you could try it. But especially if you're working with like these microcontrollers, it's good to like work on like that Android network, like what we were doing with the Meta Quest. Okay, so we covered like this configuration of OSC. That's going to look pretty similar in each application. In Macs, for example, you can see that if we want to send data, we have to tell it an IP address and a port. Another way of saying localhost is 127.0.0.1. This is essentially the same thing, except we're sending on port 7001 here. When you were receiving data, you don't have to give it an IP address. You just have to tell it which port to receive on. So you can see that 7000, this receiving here, matches with this 7000 that we're transmitting on. Right, so just very important, like if something's not working, that you make sure that you're sending to the right port and to the right IP address. So back to our script. This public OSC transmitter object just pulls in those details from this game object here. Right? Just drag that OSC settings over from here. Okay. So we have our other object here, right? So we have our primary object, which transmits the data. And then we have this, just this cube. There's nothing on this cube, it's just a dumb cube. Nothing special about it. And what I've done is I've just dragged that dumb cube over onto this other object slot so that this smart object, the smart cube, knows what to look for to calculate the distance. Okay, and so now this looks, I don't actually know why this is protected virtual void, but we know what the void update function does, right? This runs every frame. And I just took this from the OSC example. It had protected virtual void start function. It was sending an OSC message on the start function, but I wanted this to happen in the update function. So I want this to happen every frame. What I wanted to do is I wanted to check if the other object's mesh renderer is enabled, right? Makes sense, because we remember how we were checking, how we noticed that if the AR image target recognizes the image target, it will turn that object's mesh renderer on. So if the other object's mesh render is on and this game object's mesh render is also on, right? This operator right here checks to make sure that both of these conditions are true. If both of those conditions are true, then what we're going to do is we're going to create a new variable called d, and we're going to calculate the distance between this game object and the other game object, right? Calculate the distance between this game object and the other game object every frame. So we have that distance stored in this variable. Vector3.distance is a nifty function inside of Unity, built inside of Unity, that calculates the distance between two vectors, two three-dimensional or two-dimensional vectors. And that's really important for, maybe triggering something when two things get close enough. Okay. Maybe they can't have colliders on them. And so this is another way to figure that out. Or if you need like a smooth kind of like, maybe you need something to get like louder as two things get closer to each other. Calculating the distance between them every frame, you can assign that inverse magnitude to be loudness, for example. Okay, so with that distance being stored there, what we can do, what we end up doing is we create a new message, a new OSC message at this address. And we add this distance value to that message. Okay. And so this funky syntax here comes from this package that we download, that ext OSC package. Okay, this is how they implement this OSC stuff. So it's not super, important. I pretty much copied and pasted. I think the way that they had it, I think it was a string, and inside here was like hello world, but I wanted to send an actual value. So I changed this from string to float, and I changed the value to be this value that we're creating here. Okay, then it sends that message. Again, this is just from this package that we downloaded. And then it prints out the distance to the console. Not super necessary, but just it's nice to have to know it's working. To know that it's actually, to see if it's actually calculating the distance between these two things. Once you know that it's working and you're receiving those messages in Max or your other software, you can go ahead and delete that. We don't need to waste those resources by printing this data twice to the console. And that's it. So, well, I'll open it up for questions, but just a final note. This is kind of maybe like the most important part here, right? I decided to calculate the distance between two cubes and send that message. But these 3 lines of code here and this address thingamabob here, string, are the most important parts, right? So you need an address. You need to, like, if I was, maybe like, okay, we're going back to Foucault's example of like the Bach fugue. It is maybe what we do is there is an address for setting the speed that the fugue runs at. You might say speed. You could even just do this. We don't need the extra 1. So as these 2 cubes get closer together, this number gets higher and it increases the speed in Max. Maybe there's a message that changes the key, to A or A minor or something like that. And instead of sending a value to the key address, maybe we're sending a string and it's A minor, something like that. or maybe it's just sending, yeah, some message, like maybe it's sending this message, change key. And then in Max, you handle, or whatever application you're using, you randomize the key based on this change key message. Okay, this would send a bang when it receives change key to the key address, right? So this will change it between 0 and 11. And you can assign that to A, B, C, D, or 12 tone, you know, Western, you know, note series there. This isn't, is this an assignment? No, it's not an assignment. This is just to get you thinking about how you might, you know, obviously connect these different softwares together. For people who are, you know, hoping to blend Unity with lights, with physical objects like a toy controller, like sound, multi-channel sound. You know, Max handles multi-channel sound really, really well. So if you want to, you know, one thing it was doing at one point was like having an image target represent each speaker in a space, and using another image target to control how loud that sound is in each speaker, right? Oops. Let's see all my errors here. Okay. Yeah, so an image target represents each speaker, maybe 4 speakers. And you have another image target represent the sound source. And as it gets closer to each image target, that sound gets louder in a different speaker. One way of thinking about spatial audio and AR stuff. All right. What are people thinking in their heads over here? Threw a lot out there. It's recorded. Big takeaways is that there's not that much code or anything that goes into it, just a bunch of like knowing how all the pieces fit together. Fukuo, yes.
Yes, I have a question about Max. I think we need to get a license key or something. It's available at IDM, but my previous one expired. I think, could you help us get that?
I don't know if I'll be much help. Oh yeah, so like what I usually tell people is just create a new email, and I've talked with them before with classes, and they've said, hey, just do the trial, and then when your trial runs out, create a new email address and a new account, which is annoying, but it's free.
I think previously I'm in Catherine's class. She helped us get a key from IDM. It granted access via an app called Key Access. And
Okay.
yeah, through that Key Access app, we need to type in somewhat like an URL address, but not an URL into the Key Access, and then we can use Max.
Okay. Cool. That's awesome.
Yeah.
I didn't know that. I can ask
Yeah, it's just
Todd or Luke.
yeah, I think the seats are limited, so like previous people get kicked out. But I think now we have a reason to have those seats.
Yeah. Yeah. Okay. I'll ask Todd. I'll email Todd and Luke tomorrow.
Thank you.
Yeah. Didn't know that. That's cool. Key access. Okay. I'm gonna stop recording.